Good day, everyone. In this video, we are going to discuss about KNN, or K nearest neighbor for classification. So nearest neighbor na algorithms are among the simplest and supervised machine learning algorithms and have been used or well studied in the field of pattern recognition over the last century. So while these algorithms are no longer as popular as they once were, still they are very widely used in practice, and I recommend that you at least use this algorithm as a benchmark as you develop more sophisticated models. So just like me, KNN is a lazy algorithm, but of course it's just a joke, but the part wherein KNN is a lazy algorithm is not. But why is it considered as a lazy algorithm? So KNN is an algorithm for supervised learning. In other words, the data is labeled such that it simply stores the labeled training examples during the training phase. So as you can see here, we have a number of samples M, wherein we have a pair of X features with its corresponding label. So what it means to be a Bayesian algorithm is that the processing of the training examples is postponed until it makes predictions. So again, the training consists only of the stored training examples. So if you remember in linear regression, what we had was we built a linear model, right? Wherein we estimate a parameter theta or the parameter the weights. So, and in order for us to estimate the optimal na theta or weights, then we assess that using a specific na cost function. And of course, that cost function must be minimized so that we could achieve better na predictions, right? And we do that by learning or training the model, okay? But KNN, on the other hand, doesn't have any cost function and it doesn't have any learning as well. So it simply does nothing except storing the training data. Okay, so if that is the case, how does it make predictions then? So in order for us to make a prediction, in other words, predict a certain class label, then KNN finds the nearest neighbors of a query in a point and compute the last class label or classification based on the most similar points. So in this example, we have here different points that may be classified as class A or class B. So if we have, let's say, a new point, would it be classified as A or B based on the closest neighbors? So in a case where we consider only 3 neighbors, say 3 neighbors, as you can see, this new point has more similarities with class B or the green points. But if we consider more points or more neighbors, let's say 6 neighbors, the new point is essentially more similar with class A or the blue points. Okay, so let's have another example to put it more simply. So suppose we have here 2 features that is visualized in a feature space, wherein we have samples that may be classified as label 1 or label 2 or label 3. So assuming that we have a new query point, say we introduce a new point. So how would it be classified? Would it be classified as label 1 or 2 or 3? So if we consider only the closest neighbor or the closest point, so it will be classified as red, okay, because it is closest to red. However, if we consider other neighbors, it is mostly similar to yellow, okay? So as you can see, even if it is closest to red, but it is more similar to, or it is mostly closest to most of the yellow na points, okay? So To classify an example D, then we find the K, the nearest neighbors of D, and choose as the label the majority label within the K nearest neighbors. But how do we find or measure the nearest? So we can do that by computing for the distance. So one of the most commonly used distance for measuring how far a certain point from another point is the Euclidean distance, or the L1 distance. Okay, so essentially, if we have 2 points with each with having several features, a sub 1 to a sub n, and the other point having b sub 1 to b sub n. So to measure the distance, is we simply take the square root of the squared differences between the features or weights. So we have a sub 1 minus b sub 1 quantity squared plus a sub 2 minus b sub 2 quantity squared until the squared of a sub n minus b sub n. Okay, and we take the square root at the end. So in hindsight, the KNN, as we have already mentioned, is lazy, wherein it does not have any cost function, it does not have any learning, it does not have any explicit training step, and defers all the computation until prediction. The non-parametric, it is also considered as a non-parametric method because there are no assumptions that are made about the functional form of the algorithm. So for example, we don't assume that the data is linear or that the data is nonlinear, etc. So if you want to understand more or review the difference between parametric and non-parametric, so just click this link and view my video. Okay, and moving on, the KNN is also considered as an instance-based or a memory-based algorithm because, as you have seen, instead of devising one global model or approximation of the target function based on all of the data points, what the KNN does is develop a local approximation for each data point. So in other words, the local approximation then may depend on the data point itself as well as the training data points. So for instance, if we wanted to classify the label of this point, then the approximation will be local to the neighbors that are close to it. Okay, and for instance, if you have another point here, so the approximation will also be local to the points close to this. And in cases, let's say if we add more points, for instance, right? So the approximation for this data point will not be affected, but for this, the approximation will be drastically changed. So as you can see, let's say if we introduce more points here of red, then it will no longer be classified as yellow, but as red. So again, the approximations are local to its neighbors. So yeah, in short, the prediction is based on the comparison of a certain point or a certain query point with data points in the training set, rather than a global model. So in this case, it is considered as an instance-based or memory-based. So after introducing the concept of KNN, so let us see a more technical description. So this is a naive algorithm for the nearest neighbor algorithm. So for the training set, so we simply store the training examples with pairs X features with the corresponding Y labels. And then for the prediction, is what we do is first initialize a closest point and the closest distance to none and infinity. And for each of the samples in the training set, we compare or compute for the distance between a certain query point X sub Q with each of the data point in the um in the training set. And if for a specific na I, for instance, for a specific na sample, if the computed na distance is less than the closest na distance, then that current distance will be the new na closest na distance, and that closest point will then be x sub I. So the distance may be computed using an L1 or Euclidean na distance, wherein we simply compute for the square root of the squared na differences between the features. So assuming we have these points, so for the training, we simply store this each na sample points x with the corresponding labels, okay? And then suppose we have a query point or new point. So what we do is we are going to compute for all of the distances between the query point and then each of the samples, and we are going to compare or sort the distances by ascending the order. Okay, so those that are with the minimum na distances will be considered as closest to the query point. So let us move on. So these are some of the other distance metrics that you can use. You already introduced the L1 or Euclidean, and we also have the Manhattan distance, which is simply the absolute na value between the difference between the 2 points. And we also have the Minkowski na distance, which is just a generalized version of the Manhattan and the Euclidean. And then we also have the cosine similarity, which is just the dot product between the two vectors that is being normalized by their magnitude. So you can read more about this in the textbook. So let us try to understand it. So suppose we have this query point and it is in 1, 1, let's say in this points 1, 1. And then we are going to iterate through all of the samples. Suppose starting with this x sub 1 that has points 5 and 5. So first is we are going to measure the distance between these 2 points, x sub 1 and then x sub q, which is our query point. So we do that by using the Euclidean distance. So essentially taking the difference between the 2 points, squaring it, right? And taking the sum. So we have 1 minus 5 quantity squared plus 1 minus 5 quantity squared and taking the square root. So it is equal to 5.66. So we now have the current distance, which is 5.66 for the first sample. And now we are going to compare it with the closest na distance. So at this point, the closest na distance is infinity. So since this is true, this point will now be the closest to the query point, okay? And the closest distance is 5.66. And the closest point is x sub 1, which is the first na sample. And now, next na point. So assuming the x sub 2 has points 3 and 1. So next we are going to compute for the distance between the query point x sub q and x sub 2, and using the formula for the L1, it results to 2. Okay. Now comparing the current distance with the previous with the distance between the query point and the previous point x sub 1. So is 2 less than 5.66? Since it is true, then it will now be considered as the closest distance, and the closest point will now be x sub 2. Okay, so this will continue until we iterate through all of the samples. Suppose we have the breast cancer in a data set. So I just reduced here the number of features for the sake of visualization. So we have, let's say, the diagnosis, which could either be M or D for malignant and benign. And then we have several features, x sub 1, x sub 2, x sub 3, which is the radius, texture, and perimeter na mean. Okay, so we have several na samples. And let's say we have a query point x sub 5, and we want to predict the label of this tumor. So what we are going to do is to compute for the distance from each of the other na points by using the L1. So essentially, is as you can see here, taking the difference between the radius na mean, and then taking the difference between the texture mean and then the perimeter mean. And this is just for the first na sample as well as the query na sample. So we are going to do that with the difference between the x sub q and all of the other points. Okay, distances for classification. So it's pretty much straightforward. In the classification setting, the simplest na incarnation of the KNN model is to predict the target na class label as the class label that is most often represented among the k most similar na training examples for a given query point. So in other words, the class label can be considered as the mode of the k training labels or the outcome of a plurality na voting. So what we do is we sort the distances, and then we obtain the k nearest na neighbors, and then with the minimum distances, and we identify the labels of the k nearest neighbors, and the most represented and target labels in the k nearest neighbors will be the predicted na label. Okay, so here's an example. Suppose we have chosen k equals 5. Okay, and the target na labels of the nearest na points are D, M, M, B, and M. So this is not representative of my political na choices. Okay. So anyway, B for malignant, B for benign, and M for malignant. So since we have majority of the target na labels is M, so the predicted na Y for the query point is malignant or M. But if K is equal to 6, then majority is also malignant. So we choose M as well. Suppose K is equal to 1, or we only have a one neighbor. So since the closest the neighbor's label is benign, so our prediction is also benign. So in cases wherein, let's say, we have a tie, so as you can see, we have a vote for B and we have a vote for M. So in cases like this, we are taking the plurality na vote among labels. In cases where we are taking this plurality vote and results to a tie, so what we can do is to use an odd number to have a tiebreaker. So what about for the decision boundaries? So the decision boundaries are places in the feature space where the classification of a point, for example, changes. So in this case, wherein we have three labels, label 1, label 2, and label 3, what would be the decision boundary? So KNN gives locally defined the decision boundaries between two classes. So we have a boundary between label 1 and label 2, another boundary between label 2 and label 3, and another boundary between label 1 and label 3. So assuming a Euclidean distance metric, the decision boundary between any two training examples, A and B, is a straight line. And if a query point is located in this decision boundary, like for example, it is located here, it means that it is equidistant from both training examples A and B. So while the decision boundary between the 2 points is a straight line, the decision boundary of the nearest neighbor algorithm on a global level, considering the whole training set, is a set of connected na context na polyhedra. So here's another example with two classes, 0 and 1. So what would be the decision boundary? So the partitioning of the regions on a plane is in 2D is also called as the Voronoi diagram or the Voronoi tessellation. So, and it may be obtained using triangulation, wherein we connect the centers of the circumcircles. So in order to draw the decision boundary of the two-dimensional nearest neighbor classifier, we take the union of pairwise na decision boundaries of instance with the same class. Okay. So now how do we select the best na K or optimal na number of neighbors? So in practice, the values of K between 3 to 15 may seem reasonable na choices. Also, if we are working on binary classification problems, it is a good idea to avoid even numbers for K to prevent ties. So in some literatures, the K may be computed from the square root of n, where n is the number of samples in the training data set. So there is also an impact of choosing K. So having a small k, or let's say k is equal to 1, so the boundary or decision boundary may be minimally restricted. So the KNN models are said to produce low bias, but high na variance. Okay. And as we increase the value of K, the flexibility of the classifier gets reduced. Okay. And then, so that means the model is becoming less na complex, right? And then, because we are increasing the flexibility of the classifier, the decision boundary gets closer and closer to linear. Okay, so these models produce low variance but high na bias. So neither perform particularly well based on test accuracy. So we need to find a model with well-balanced variance and bias. And we can find that model through parameter tuning.